Hey, good afternoon. This is Heather Archambault. I'm a program manager in the Climate Program Office, the Modeling Analysis Predictions and Projections program. And I'd like to welcome you to our monthly MAP webinar series. The topic of today's webinar is Persistent Flow Regimes and Extremes. And this webinar is being co-sponsored by the Office of Weather and Air Quality, or OWACS, Earth System Prediction Capability Program, which is led by Jesse Carman. And today we have three excellent speakers. The first will be Tim Willings from the University of Oxford. He's going to talk about where and why the frequency of atmospheric blocking may change in a future climate based on climate model projections. Then we'll be hearing from Hailan Wang from NASA, and she'll be discussing dynamical and thermodynamical causes of the rapid onset of a severe drought over North America in 1988. And then finally we'll close with presentation by Stan Benjamin from NOAA Earth System Research Lab, and he'll be discussing subseasonal predictability and frequency of blocking using a coupled atmosphere-ocean model. So just some logistics before we start. After each talk, there will be a few minutes for discussion. If you'd like to ask a question, hover your cursor over the green tab on the top center of your screen that says Viewing Climate Program Office. You'll see some text there. If you click the Participants button and then the Raise Hand logo, a little hand logo will appear next to your name in the attendee list. And then when we finish each talk during the Q&A session, your line will be unmuted, and then you can ask your question. So with that, we'll jump right in. And it's my pleasure to introduce our first speaker, Tim Willings from the University of Oxford. Tim earned his PhD in meteorology from the University of Reading. And he stayed on in Reading for a postdoc, then a fellowship, and then finally a lectureship. And now he is associate professor in atmospheric physics at Oxford. And Tim is an expert on large-scale atmospheric dynamics, and he works on topics related to the weather and climate of the North Atlantic European sector. And his interests lie in basic understanding of dynamical features such as the jet stream, storm tracks, and large-scale regimes such as blocking and the North Atlantic Oscillation. And he's interested in how these features vary in time and respond to forcing such as that from anthropogenic climate change. So, Tim, I will now see if I can transfer controls to you. And great. Can you hear me okay?
Yeah, I can hear you.
Okay, great, and we can hear you, yes. So we can see your screen, not quite your slides yet.
Okay, so I've now...
Perfect. Thanks, Tim.
Okay, brilliant. Thank you. Thank you very much, Heather. Thank you for the invite to take part in this. Thank you for your kind introduction. So yeah, I'm going to talk about blocking and climate change. Okay, so what is predicted to happen to blocking in the future, mostly? How confident we should be in those changes? And I guess I'm going to end up particularly talking about blocking impacts. So the impacts that blocking has, particularly on temperatures, and whether we should have some confidence, actually, slightly paradoxically, in how that changes, that impact changes. So I need to thank lots of people who have done a lot of the work that I'm going to show you now. There's a big list on the screen of people who have contributed to this. So first of all, I'll just give a very brief introduction to what I think of as blocking. Okay, so blocking is essentially a persistent flow pattern. Okay, it's a weather regime that tends to kind of block the storms and the westerlies as they progress across the ocean basins. So in this on this slide, we've got a couple of pictures at the bottom. Both of those pictures are basically 2-week averages of some winter periods. Both of them around Christmas time from some different years. So the colours show the stream function at upper levels, averaged over these 2 weeks, and and all the little dots show the individual cyclone tracks that happen during those periods. So in both cases, we've got quite a large-scale disturbance over the Atlantic and Europe that's acted to divert all the blocks and divert all the storms away from Europe. In the first case, they've all been diverted to the north, north of a kind of a wave-breaking structure. In the right-hand case, there's a cut-off high, and lots of the storms are stopped just upstream of that. And I like showing this picture because these are the two events look quite different, and these are actually both they're both events that are picked up by the kind of blocking indices that we use. So we generally use indices like the Tibaldi-Molteni type of index, which looks for a reversal in the usual meridional gradient of some field, either geopotential height or potential temperature or something like that. I'll probably show a mix of indices today, but they're basically always indices that are looking for a reversal in that meridional gradient. And we have a little picture on the top just to show some impacts of blocking. The UK doesn't always look like this. I have to say this was a very unusual event. And we'll talk about it a little bit more later on. I guess one of the special things about blocking is it often exaggerates the weather in each season, right? So it can bring really cold spells in winter, like this example, but also really severe heat waves in summer. So it can have damaging impacts in both seasons. So moving on now to talk about the projected changes in blocking. Okay, so we use climate models to look at future changes in blocking, and of course we always have to bear in mind that there are problems with climate models, and these are very well known biases that have been around for many generations of models. Essentially, many models still have too little tilt in the jet and the storm track as they come across the Atlantic in particular. The right-hand picture is quite an old picture now, showing a particular contour of geopotential height, and it's just to indicate really the difference between the models, which are all the green lines, and the black line, which is the observations, showing that the observations have a much stronger tilt across the Atlantic than all the models. So we have a systematic bias with the zonal winds being too strong and too zonal. And in general, in models, we don't have enough blocking. That's a fairly well-known problem. So bearing that in mind, we're going to talk a bit about the projected changes. So the figure on the bottom left shows the multi-model ensemble mean projection of future blocking change from CMIP5 models. Okay, so lots of different models have gone into this. And the models actually generally agree pretty well that we're actually going to see a reduction in blocking in the future. We obviously have to think about whether, how much we should trust that, but the models do agree actually on the sign of the change in blocking. Now, there's been a lot of discussion in recent years about the effect of the Arctic. So as the Arctic warms particularly strongly, there have been suggestions that this should lead to more blocking and related features. So what we're looking at now actually is still looking at the future. Okay, so these are some experiments that we did looking at the end of this century, the end of the 21st century, to see what is the effect of the Arctic warming. So we designed a set of experiments to kind of represent the uncertainty in future changes. Okay, so for example, the sea ice figure in the top right, this is showing the difference in the sea ice forcing between a run that we did where the Arctic warms particularly strongly, that's what we call Arc plus, and then a run where the Arctic warms particularly weakly in the future, that's what we call Arc minus. So these were the kind of experiments we were doing. So the bottom row of figures shows the response to having a particularly warm Arctic in the future. So we can see in the cross section we have a kind of a local warming over the Arctic. In Z500 in the middle we have higher heights over the Arctic, and we have a very clear reduction in the storm track activity at high latitudes. So certainly the uncertainty in current models in how much the Arctic will warm in the future does play through to uncertainty in the circulation response. So that picture showed the storm track now I'm going to show you the actual blocking in these simulations. So hopefully, if you're looking at the same thing as me, you should have three maps here. So the map on the left here, I don't know if you can see the cursor, is our kind of all four things type simulation. So this is an A1B run for the end of the century. So we see some reductions in blocking, but it's a fairly weak signal in this model. And then the map in the middle shows the difference between our warm Arctic run and our cold Arctic run. So if the Arctic warms particularly strongly in the future in this model, then we see a stronger reduction in blocking over Europe in particular. Okay, so having a warmer Arctic actually leads to less blocking in the future. However, the one thing to mention is that the picture on the right is from a different set of experiments, where instead of just warming the Arctic, we warmed uniformly. So we warmed the sea surface temperatures everywhere uniformly. And what that actually does is through the moist feedbacks, that gives us a particularly strong warming in the tropical upper troposphere. And so that changes our upper level temperature gradients, as opposed to our lower level temperature gradients, which are associated with the Arctic warming. And in this we get bigger reductions in blocking. So perhaps as we should expect, really, the changes in blocking are actually more sensitive to the upper level changes, which are associated with the tropics, rather than the lower level changes, which are associated with the Arctic. So let's connect briefly to observations. Are there actually any observed trends in blocking? So Livy Barnes led a paper a couple of years ago now, where we looked at several different reanalysis data sets, several different methods of describing blocking, and all the different seasons. And we actually found very, very few significant trends, no more really than you'd expect to see by chance. So I don't think there really is any evidence that there are kind of consistent trends in blocking going on. So what I want to talk about then, just for the end, is the changing impacts of blocking. Okay, so we've said that the models have biases, so we're not sure how much we should trust them, and there is also uncertainty coming into the future projections of blocking, because we're uncertain how much the Arctic will warm, and we're uncertain how much the tropics will warm. So given all this uncertainty, can we actually say anything about the impacts of blocking in the future? I think actually, slightly paradoxically, we can, because there are some fairly simple mechanisms at play here. So what we're looking at now is we're looking at some composites of blocking events in the CMIP5 climate models. And actually, this is just a subset of the models. These are the four best models in terms of blocking out of CMIP5. So on the top row, we have some composites of Atlantic blocking. Okay, here we have the high pressure. The contour lines are the geopotential height at 500 millibars. So we have the high pressure over Greenland and a low to the south. So we have a block in the Atlantic, and this is essentially a classic negative NAO pattern. The colours are the surface temperature anomalies. Okay, so relative to each individual run's climatology, these are the anomalies in the 2 meter temperature. So under the anticyclone, we have high temperatures, but around the edges of it, we have cold temperatures over lots of Europe and North America. Now, the left-hand picture is for the 20th century simulation, and the right-hand picture is for the end of the 21st century, so in the future. And hopefully what you can see here is that the temperature anomalies are much weaker in the future. Okay, so with respect to the future climatology, we're getting weaker temperature anomalies as a response to blocking. And then the bottom pictures show the same thing, but for composites of European blocking. So again, we have a high pressure in both cases over Europe, and we have temperature impacts associated with that. But the cold temperatures that spread over Europe during present day blocking those cold anomalies are much, much weaker in the future. So one thing I forgot to mention is that these are all winter cases. Okay, so there's a fairly clear signal that the temperature anomalies due to winter blocking are going to weaken. Okay, so what's going on here? I think it's a fairly simple mechanism. If we go back to this very unusual event for the UK, we can see the Z250 map on the left. So the UK was essentially in this stream of cold air coming down from the north, and a lot of the temperature impacts that we get from winter blocking are just due to thermal advection. Okay, so the U dot grad T, we have a wind anomaly blowing over a temperature gradient, and that's what gives us a lot of the temperature impacts. So if we think about how some of these things are going to change in the future, we're a bit uncertain about the wind anomalies. Okay, we have to think about how much we believe are blocking in the models. But actually, we can say some quite robust things about the temperature gradients, the mean temperature gradients. So these maps, the top maps, just show the climatologies of surface temperature in winter on the left and in summer on the right. And then the maps at the bottom show the kind of projected climate change response in terms of the temperatures. And the thing I'd like to highlight here is that in the winter, the places that are cold in the current climate, so the continents and the Arctic, those are the places that warm the most in the future. Okay, so that means that all of the temperature gradients are essentially predicted to weaken in winter in the future. Whereas in summer, it's a lot weaker, but it's the opposite, where the continents which are warm to start with, again, warm the most in the future. So horizontal temperature gradients are expected to increase in the summer. And so I think this is what is going on in the winter blocking cases we've looked at. We're getting much weaker temperature anomalies because we have the same wind anomalies, but those are blowing across a weaker mean temperature gradient. So we tried to look at this quite generally using a regression model where we assumed that we had no change in the wind statistics, but we have these consistent changes in the mean temperature gradients. So the top pictures here show the standard deviation of temperature in winter and summer in present day simulations. This is the change. So this is the future simulations minus the present day. So, for example, we see decreased variability in winter in the extratropics. And in the bottom, we can reproduce some of this in coastal areas just by taking the change in the mean temperature gradients. So I think I should probably wrap up. So first of all, there aren't really any clear observed trends in blocking occurrence. It's a very noisy thing to measure in any case. But in the long-term future, models do predict a reduction in blocking, largely kind of attributable to mean state changes, although we should be a bit careful about cause and effect there, I think. Changes in upper level temperature gradients seem to be really key for how the blocking changes in the future. The Arctic warming has an effect, but it's weaker. The models do predict fairly robust changes in the temperature impacts, in particularly weakening of the temperature anomalies in winter. And I think these changes are actually quite robust, and we should probably have quite a bit of confidence in them because it's ultimately a fairly simple mechanism due to the thermal advection. Okay, so I'll stop there, and thank you for your attention.
Tim, great. Thanks so much. So now I'll open up to questions. First, are there any questions for those in the room?
So, with the warming of the Arctic, there isn't a mean decrease in the jet stream in the zonal jet that would result in more meridional flow, and I guess it's sort of interesting result.
Yeah, not really. Oh, hello.
Tim, yeah, you cut out for a second. Go ahead.
So not really, not in this model at least. I mean, we see a bit of a weakening of the winds on the poleward side of the jet stream, but we don't really see the whole jet weakening that much. To be honest, we see weakened storm activity on the poleward side. So it's a bit more, I guess the response is a bit more kind of regional than the big hemispheric changes that are often talked about.
Other questions in the room? All those questions? Okay. Are there any questions online? You can write a message if you have a question, or you can raise your hand. And hopefully I'm not seeing anyone here. Okay, so for right now I don't see any questions, but if there are any questions, don't hesitate to chat or put your question in the chat box, and we'll be able to get to those at the end if there's time. So, Tim, thanks so much for your presentation. That was really excellent, and if you don't mind, maybe you could stay on till the end. I know it's getting a little late there for you, but...
No, it's fine. It's fine. The kids are in bed now, so it's okay.
Okay. Okay, sounds good. Okay.
Do you need
so, yeah, you can stay on. I'm transfer control now. Okay, so the next speaker, Hailan, can you... Oh, you're sharing. Great. Hi.
Can you see my slide?
Yes, we can. Let me just look through bio. Okay, so our next speaker is Hailan Wang, and she's going to be discussing a drought-related research project that's supported by the MAP program. And let's see, I hope I have the most up-to-date bio for you. I think I do. Okay, so Hailan, she's a lead scientist at SSAI, Science Systems and Applications, Inc., and she's affiliated with both the Global Modeling and Assimilation Office at NASA Goddard Space Flight Center and also NASA Langley Research Center. She obtained her PhD in atmospheric sciences from the University of Illinois at Urbana-Champaign, and Hailan is a co-chair for the National Integrated Drought Information System, or NIDIS, Predictions and Forecasts Working Group. And that group coordinates and facilitates transitioning drought prediction research to improve NOAA operational drought outlooks. And she's also a member of the NOAA Drought Task Force, which is organized by the MAP program. And her research interests are broad climate variability and predictability, weather and climate extremes, the global water and energy cycles, and global climate, or AGCM modeling of the Earth's climate. And with that, Hailan, you can begin whenever you're ready.
Okay, thank you, Heather. First of all, I'd like to thank Heather for providing such a nice opportunity to present our work, and also very much appreciate your coordinating effort. In my talk, I'm just going to switch to a different region, North America, and kind of focus on the circulation anomaly that will drive the drought over North America. So just specifically, I'm just going to talk about one of our recent studies on drought, just looking into the role of stationary reservoir winds for the warm season drought development of North America. And here, of course, I would like to acknowledge the support from the NOAA MAP project, and also like to acknowledge my co-authors, Stephen Schubert and Randy Coster from NASA GML. So our study just really just motivated by the fundamental need to better understand the processes that drive North American drought during warm season, and to explore potential sources of predictability, and with, of course, the ultimate goal of improving operational drought prediction. So recent studies show that during warm season over North America, the year-to-year variation of the surface temperature and precipitation, along with many other surface meteorological fields, are really just mostly explained by the atmospheric internal variability processes other than SSC instead of SSC. So what is shown in this slide, the estimation based on the 5 current AGCMs using their respective image simulations. And the fields, the quantity shown here, just the ratio of the variance, the year-to-year variation of surface temperature, and precipitation just due to the year-to-year variation of seasonal SSC divided by the total variance. So they just kind of indicate to what extent the SAT variation might be important in explaining the year-to-year variation of surface meteorological variation. And if we focus on North America, we can see that the SST, seasonal SST variation, can only explain about 10 to 20% of the year-to-year variation of surface temperature and over much of the North America. And as for the precipitation, the SST only explains about 5 to 10%, and that contribution is primarily limited to the west portion of the North America, with close to zero contribution over the rest of the North American regions. So basically, just for North America during warm season, the weak contribution from SST and of course at the same time the predominant contribution from the processes other than SST, such as atmospheric internal variability, just promotes a very strong need to better understand the processes other than SST and also explore potential sources of predictability other than SST. And this is where our study on stationary Roswell waves just came in. And also I want to mention that our study is actually also based on the past studies such as Newman, 1998, Schubert et al., 2011, and these past studies suggest that over North America, the warm season drought development can actually, for some events, can actually be initiated and sustained by some quasi-stationary circulation anomaly, which are essentially originate from the stationary Roswell wave propagation. So just to get started, we can just first of all take a look at the leading modes of the subseasonal circulation variability. The reason we focus on subseasonal timescale is mainly because the impact of these stationary Roswell waves on the drought development over North America during warm season primarily occur on the subseasonal timescale. So these leading modes of subseasonal circulation variability can be obtained by performing a rotated UF analysis of the summertime subseasonal upper-level view wind. And here, our analysis just used the data from NARA, and the subseasonal anomaly just was obtained by computing the departure of the monthly anomaly from the seasonal mean anomaly for summertime. And what is shown right is the top 5 rotated UF distribution. And here, if we just only focus on North America, focus on these leading patterns that would impact North America, we would have this second, third, fourth, and fifth mode. And I'm not going to spend much time to dig into detail about these spatial patterns. I just want to point out the important role of the North Hemisphere mean jet stream in guiding these leading patterns of the subseasonal circulation variability. And if we want to connect all these leading modes of subseasonal circulation variability to the actual climate events, we can take a look at the temporal distribution of the rotated principal components as shown on the right. And here I just kind of bring out several key climate events, drought events, during which the stationary Roswell wave play a role. And one such example will be the June 1988. Basically, the monthly anomaly for this month has strong projection, both second mode and fourth mode. And we know that, as I'll show you later, this month, the quick rapid development of dry condition during this month actually plays a very important role in leading to the rather severe 1988 North American drought. And we know that throughout the history of North America, the 1988 North American drought is one of the costliest and also one of the most severe drought occurred out there. So just to get started, if we're just going to focus on the 1988, we can first take a look at the monthly anomaly, just shown right. And here the upper level V1 and surface temperature just taken from NARA, and precipitation and surface soil awareness just taken from Maryland. So we can see that if we just kind of focus on North America, we can see that in the upper troposphere at 250 millibar, we have this very strong southerly anomaly to the west and strong northerly anomaly to the east, just corresponding to upper level high anomaly just centered over central North America. And then beneath this very strong upper level high anomaly, we have very strong surface warming anomaly developing over the central portion of North America. And in terms of monthly mean, the magnitude actually exceeds 8 degrees Celsius, which is quite enormous. And if we turn to precipitation and surface soil awareness, we can see that a pretty strong precipitation deficit and surface dryness anomaly got developed over the eastern portion of the U.S. And notice the longitudinal shift between the surface temperature anomaly and precipitation along with the soil dryness anomaly, just mainly because the atmospheric circulation anomaly over North America exhibits some westward tilt with height. And that kind of explains their shift in terms of their longitudinal location. But if we really want to have a better understanding on how the extreme dry condition in 1988, especially in June 1988, got developed just quickly as a result of these quasi-stationary circulation anomalies that originate from these stationary Rossby wave propagation, we have to turn to the daily anomaly, as shown in this slide. So what is shown here is the temporal evolution of the daily anomaly with data again taken from Mara and Maryland. And the left panel just shows the temporal evolution of the upper level V wind, average between 40 north and 60 north, with 10-day running mean applied, just from May 1st to July 31st. So you can see that during this 3 months time period, we actually had 2 stationary Rossby wave events developed. And some projection analysis just shows that the first event had strong projection on the second rotated UF, which is showed in the previous slide. And the second, this event has a strong projection on the false mode. And that's why when we take a look at the monthly mean data, we saw the strong projection on both the second and the false mode. And also want to point out that once established, these quasi-stationary circulation anomaly can remain there, especially over North America, for several weeks. And at the same time, even though these circulation anomalies remain quasi-stationary, there is quite distinct eastward wave energy propagation. For example, just take the first event, for example, appear originate from the Western Pacific, and that actually has been suggested in some previous studies, such as Chen Newman 1998, who point out that this stationary Rossby wave appear to originate from some convective anomaly over Western Pacific. And then you can see the wave energy propagation across North Pacific and then North America. And here we have the peak magnitude of the circulation anomaly. And then further propagation eastward across North Atlantic. And even though not shown in here in this plot, we actually had further downstream energy propagation just to Europe and then northern Russia. And then if we compare the right 3 panel with the left panel, we can see that very quickly, just within about 1 to 2 days of the arrival of this quasi-stationary circulation anomaly over North America, we had very strong surface warming anomaly, precipitation deficit, and surface soil dryness developing over central portion of North America. And of course, even though there were some weather events that led to anomaly of similar sun during the prior time period, but in terms of magnitude, they cannot be compared with the impact of these stationary Rossby wave events. So next, in the rest of the talk, I'm just going to focus on this event, and we're just going to perform a case study for this event, and we hope that through such case study, we could look into or have a better understanding of the processes that led to rapid drought development over North America, and how important it is to represent these various processes in the context of the model handcast. So here's just a list of the 4 processes or factors we're interested in. The first one is the stationary Rossby wave sources over Western Pacific. This has been suggested in previous studies I just mentioned just now. And also the North Pacific mean jet stream, how important it is for the model to have a faithful representation of the mean jet stream to represent the impact of the stationary Rossby wave over North American drought. And also soil moisture feedback over North America, and also the late May, the May 20th atmospheric and landing neutral conditions. And here I just want to mention that the May 20th is just the date at the very beginning of the arrival of these quasi-stationary circulation anomaly over North America. And in our study, we just use the AGCM modeling approach, mainly because AGCM can allow us to isolate and assess the relative roles of all these factors we're interested in. But when we take a look at the GEOS 5 AGCM simulation, we realized that the GEOS 5 AGCM doesn't really do a good job in simulating the North Hemisphere jet stream during warm season. So what is shown here is a comparison between MARA and the GEOS 5 image simulation in terms of the up-level zonal wind for their summertime climatology. And we can see that especially over North Pacific, the model jet is considerably weaker compared to those in MARA. It's pretty weak and also disoriented. And here I want to mention that GEOS 5 AGCM is not alone in this regard. We actually saw similar bias in many other current AGCMs as well. So in our study, to kind of circumvent this model bias in the mean jet, especially those in over North Pacific, we just performed the GEOS 5 AGCM replay. We just utilized this AGCM replay technology. I'm not going to get into much detail into further detail, the technical detail of this replay approach. Just want to briefly point out that by doing such regional replay, we are able to constrain the model atmosphere to MARA for limited regions and also a subset of all these basic variables. So we have done a series of regional replay experiments, mainly want to determine the key region that matters for the maintenance of the North Pacific mean jet stream. And we found that when we constrain the mild atmosphere to MARA over East Asia and West Pacific, we are able to remove the majority of the model bias in the North Pacific mean jet stream compared to panel A with panel C. And later investigation just shows that the poor model simulation of the North Pacific jet stream is really related to the model of the strong warming bias, the air temperature warming bias over Northern Eurasia through summer wind balance. And so if we only replay U and V, we are only able to partially correct the model jet mean bias. Right now it has relatively correct shape and latitude, but magnitude is still weaker compared to the MARA. So overall, all these regional replay experiments just suggest that they can serve a useful framework for our investigation purpose. So the constraining model atmosphere to MARA over East Asia and West Pacific not only removes the majority of the model bias in North Pacific mean jet, but also allows us to specify the observed station wave sources in the replay region. So just for our investigation, here's a list of experiments we have performed. Experiment A is really just a free-running handcast experiment, just initialized from the May 20th, 1988. And B1 through B4, just based on the regional replay framework I just mentioned. B1 has all four ingredients here we want to look into. It not only initialized from May 20th, 1988, but also through performing such regional replay, it can specify the observed station wave sources over Western Pacific. And also through such regional replay, it has a mostly corrected model mean jet over North Pacific. And over North America, we allow the land to interact with atmosphere, so we also incorporate the zone moisture feedback in B1. And in B2 is the same as B1, except that we remove this late May atmospheric and land initial condition. B3 is the same as B2, except that we disable the land feedback, the zone moisture feedback over North America, and that was done by using the 3-hourly climatological zone moisture fields for the land instead. And B4 is the same as B2, except that when we do the regional replay, we only replay U and V, so that the model jet is only partially corrected, so that the comparison between B2 and B4 can give us an idea to what extent the model representation of this stationary Rossby wave propagation across North Pacific and their subsequent effect on the rapid development of drought condition over North America may be subject to the model representation of the jet specifics, such as the jet magnitude. So all these experiments just performed using the 1-degree resolution GEOS 5 AGCM, and each experiment just consists of a control ensemble, just 31 members, just mainly just for the years 1980 to 2010. And the average across all these 31 members just used to provide the climatology for the anomaly ensemble. And the anomaly ensemble consists of certain members which only differ from each other in their atmospheric and sometimes land initial conditions. So what is shown here, just the comparison between MARA and each of the 5 AGCM experiments we have performed. And here, just to facilitate the comparison between MARA and our experiments, Here, just in these 5 panels, I just plot in contour the Mara, the Mara distribution for the -6 and +6 meter per second. So what is shown here, and all these 5 panels just show the ensemble mean difference between the control ensemble and the anomaly ensemble. So if we first compare Mara and experiment experiment A, just free-running handcuffs, we can see that just due to the model bias in jet, in which model jet is considerably weaker compared to those in the observational Mara, as a result of that, we have this westward retrogradation. And because of this westward retrogradation, at week 2, the handcuff decirculation anomalies are actually of opposite sign of those in Mara. And if we compare B1 with Mara, we can see very good agreement for the first stationary Rossby wave event, and which is just totally expected because it contains all the ingredients that are necessary to capture this stationary Rossby wave event. And if we turn to B2, remind you again, B2 is the same as B1 except that it removes the contribution from the May 20th atmospheric and land initial condition. But despite that, we can see the general agreement between B2 and Mara for this first stationary Rossby wave event. And of course, there are some displacement at about May 20, just mainly because of the absence of the contribution from the May 20 atmospheric and initial condition in B2. So the good agreement between these two is quite interesting to us. This just suggests that if a model is able to predict the convective anomaly over Western Pacific, and if the model is capable of providing a realistic North Hemisphere mean jet stream, especially over North Pacific, then we would expect the model to predict the rapid development of drought condition over North America about at least 2 weeks later. So this would have some implication to the subseasonal forecast of the drought over North America. It just indicates that a proper incorporation of the stationary Rossby waves in a model can provide the potential to extend the subseasonal handpass for 2 more weeks, because it takes about 2 weeks for this stationary Rossby wave energy to travel across North Pacific. And then if we compare B2 and B3, they are overall similar to each other, just suggesting that, at least for the time period we study, the land feedback is not important. And if we compare B2 and B4, we can see that it is important to have the correct representation of the mean jet, including the jet magnitude. Actually, the following slide just provide more details in comparing B2 and B4. So these two just copied from the previous slide. And right panel just shows the temporal average over this short time period. And it just shows a comparison between Mara, as shown in the red line. The black line shows the ensemble mean simulation, and the green line just shows the ensemble spread of the 30 ensemble members. So we can see that in the B4, because the jet is only partially corrected, so the jet magnitude is relatively weak. And therefore, over North Pacific, you can see larger spread over this region. And as a result, we don't really see a lot of signal, as shown in this case, over North America. And also, you can see because of the weaker North Pacific jet in B2, the eastward wave energy propagation is slower than Mara, just compared to B2. So this just suggests that the comparison between these two just suggests the very important role of the jet stream in guiding and constraining the wave energy propagation path and speed across North Pacific. And this is the last slide. I just turn to the temporal average mean anomaly for surface temperature, precipitation, and soil wetness, and comparison between Mara with experiment A, the free-running handcast, B1, B2, and B4. So basically, for BA, we can see that you can see the impact of the westward shift of the handcast circulation anomaly, but you can still see some benefit from the May 20th atmospheric and land initial condition used. And again, if we compare B1 with Mara, you can see the best agreement between these two. And the B2 also agree with Mara, just that in terms of magnitude, the anomaly is just not as strong as those in Mara. And this is This is understandable because what's shown here is the ensemble average across all these certain members. But still, we can see that even though we do not include the May 20th atmospheric and landing industrial condition, if we are able to prescribe or predict the stationary Rossby wave sources, and also have a faithful representation of the North Pacific mean jet stream, then we would expect to provide a nice forecast of the drought condition over North America. And the comparison between these two, B2 and B4, again, just shows the critical importance to have correct North Pacific mean jet stream. So here's the conclusion. Just want to point out that through such a case study of a station Rossby wave event, just to bring down the critical importance of the North Hemisphere mean jet stream in guiding and constraining the wave entry propagation path and speed. And also for the case study we investigate here, we see that in the presence of the very strong North Pacific mean jet stream, the convective anomalies over Western Pacific in late May actually can produce a predilection for the persistent upper-level high anomaly over Central North America about 10 days later, which subsequently lead to the rapid development of severe dry condition out there. So the implication is that the stationary Rossby waves can serve as a potential source of predictability for subseasonal development of drought over North America. Need to cross this out. So just to kind of incorporate that, it is very important for the model to have the correct Northern Hemisphere jet stream, not only in terms of location shape, but also magnitude in the AGCMs. And of course, it is very important to further assess to the predictability of the station Rossby waves, and that would include a better understanding of their origin. That's it. Thank you so much.
That's great. Thank you. Do we have any questions in the room or online? And Dan and Tim, just I unmuted you if you would like to ask a question.
I guess.
Yeah, go ahead.
I guess I could ask. This is a very selfish question. So you mentioned in the observations the stationary wave carried on to Europe. What happens in your model simulations over Europe? Do you have any signal of the right wave over Europe?
Yes, actually, we have done some work just looking into the role of stationary Rossby waves, connecting what happens over North America with what happens over Europe and also Northern Russia. We do found some important connections out there. So basically, any processes over North America that would excite the stationary Rossby waves can further propagate downstream just under the guidance of the North Atlantic jet stream, and then subsequently affect the surface anomalies over Europe and also Northern Eurasia.
Okay, thank you.
Ellen, I'm just curious, so what would you say is the more unusual aspect of this event, or what made this extreme event? Was it the unusual forcing, or was it the jet structure was conducive to this pattern, or is it possible to say?
That is a very good question. Actually, that's what we're currently investigating. It is very important to find out what initiates all these stationary Rossby waves and what processes sustain them. Right now, these processes could vary from event to event. We are hoping to find some origin that could have some predictive value. If it turns out that some origin, just purely come from the atmospheric internal variability, just inherently unpredictable, then we cannot take advantage of that. So right now, we just hope to do further studies, especially based on the observation, looking into all these climate extreme events, during which the stationary Rossby waves play a role, and just to find out what initiates. So right now, we do not have a good answer. We hope to address it in the forward.
Thanks. I do see there's a question. Karen McKinnon, I am muted.
Does this microphone work?
Yep, may hear you fine.
Oh, perfect. At the beginning, you talked about the role of, I believe you said, thermal anomalies, moreover in Northeast Eurasia, in terms of influencing the position and the strength of the jet. and said that that was why it was important to include, in addition to the UV, also the T. But I'm a little bit confused because I thought that your replay region was just the box that you had outlined, in these plots on the left. So what's the role of Northeast Eurasia in the situation?
Our results just show that in this free-running Jules 5 AGCM, the poor model simulation of the jet stream here is primarily related to the model warming bias over Northern Eurasia. So this is a jet, the thermal wind balance, true thermal wind balance. So basically, in the model, it has a very strong warming bias over here. So the meridional temperature gradient will be weaker compared to those occurring in nature, and therefore the jet will be weaker and also not so organized compared to nature. And that has been further looked into. That has been further investigated, for example, by performing a regional replay experiment in which we just constrain the model air temperature just over this region and to see to what extent the non-specific mean jet stream is corrected, and we do see the majority of the correction out there. And the reason we use this region just that it has two benefits. First one, it just do the regional replay of air temperature of this region so that the jets can be mostly corrected. And then the replay of this region, we can specify the observed sources for or observed origin for the stationary Rossley wave that we study. So basically this jet just just primarily related to the model warming bias over this region.
Okay, great. Thank you.
Thanks.
Okay, great. So now let's move on to our final presentation by Stan. And Stan, I'm just going to pass control to you. And as I do that, I'll introduce you. So Stan is Chief of the Assimilation and Modeling Branch of Esril's Global Systems Division. He's also a research scientist there, and he's also affiliated with the Cooperative Institute series. And Stan received his PhD in meteorology from Penn State, and he's a longtime fellow of the AMS, and his research interests are in data assimilation, global and regional numerical modeling, observation impact, isentropic coordinate applications, and land surface modeling. And I should mention, if Stan probably will, oops, sorry, I haven't quite, sorry about that, Stan, I didn't quite pass control to you. I should mention, and this work is sponsored by OWAC's Earth System Prediction Capability Program. So Stan, you should have control, and hopefully you're able to share your screen. And you're on mute. Sorry about that.
Okay. Are you able to see my...
Not yet.
Interesting. Okay, let's try that again here.
Stan, we went a little over before, but...
How many minutes do you want to shoot for here? There we go.
15. I think 15? We can go a little bit long, and people can off as they need to, but...
Great. Okay, so I'll push that off to the side and go into a slide mode here. Thank you. Are you able to see that okay?
Perfect.
Okay, so wonderful talks already here, and this talk also in blocking will come a little bit more from the NWP perspective at short-range forecasting. I really focus more on processes, and also the preliminary results that you see here is a key aspect because we're really just being able to start some new studies here and looking into week 3, week 4 processes related to predictability. My colleagues are sitting here with me, most of them right now, and also appreciate the connection with ESPC, as you just called out there. So obviously, as Tim and Heilan have already said here, we're looking at weather extremes here, but many of them are indeed related to blocking here. And so the Earth system prediction capability did identify blocking as one of the focus areas here because of these stationary or quasi-stationary events are so related to the key weather extremes that are important in this whole arena. So as part of ESPC, we're able to identify processes, as is known in the literature here, related to onset, cessation, and sustenance of blocking events here. And they've already come up in many of the seminars here. But then also to start to look at, well, what model components here, and this is a subjective estimate here based on studies done in the past having to do with initial condition, the need for coupling, physics issues, numerical issues, and land surface issues, and how they might come into play here toward the goal of how to identify sensitivity for predictability of these processes in blocking. So our hypothesis really it's important to identify this is a hypothesis that the predictability for overall blocking is really related to the predictability of these individual events that we've identified.
Hey, Stan?
In the slide here. Yes.
We're getting some static on your mic, I think, so it sounds like it's brushing up against something, maybe, just so you're aware.
Okay. Let's see if I can stop that here. Can you hear?
Okay, you sound good. Yep, sounds good now. Thanks.
So we have identified sensitivity to processes to these specific areas, certainly physics, resolution, numerics, and have been able to look at some initial hindcast capability here. And we know that we need to look at overall statistics through this period, but also at specific case periods here for blocking events that are identified in the literature. So we have two data sets to be able to look at the CFS version 2, which is available as part of the current North American and NOAA NMME, but also to be able to bring into bear this newer FIM-HICOM model, which uses an alternative grid structure in the horizontal and the vertical. So some of these frequency studies have started, and I'll show a couple of these very brief initial results here. Well, this is an important slide here from Thomas Jung from European Center in this project Athena that took place in looking at the sensitivity of blocking to horizontal resolution. And so Thomas was able to find out of this that being able to go to T511, around 30 to 35 kilometer resolution, was important to be able to get the overall blocking, but also that the topography was necessary to be able to do that. So that's kind of a key initial data point about resolution sensitivity for blocking frequency. So we've been able to bring to bear a new global coupled model here using an alternative adaptive vertical coordinate with largely an isentropic system in the atmosphere, then also to combine that with the ocean model, which has been developed by Navy and NOAA, especially with NCEP, also using an arbitrary Lagrangian Eulerian vertical coordinate, and then be able to match the grids here in the horizontal to be able to minimize errors in horizontal flux coupling. So this is a comparison here between CFS version 2 and FIM-HICOM, and there's a lot of borrowing back and forth between these components here, which really I think is a harbinger for the future about Earth system modeling, having this intercomparability to be able to bring these pieces back and forth. And so using the same initial conditions in this 16-year hindcast run between the two here, the physics are strongly similar, but not exactly the same, using two different ocean models here, same land surface model, and then with the direct coupling here with FIM-HICOM to be able to call the ocean every physics time step in that. So the data sets, again, that we're looking at here initially are the ones that are already pre-existing from the CFS version 2 in the bottom here, and then matched runs with this period that were done with the FIM-HICOM using the CFS initial conditions, out of which we were able to have, I guess, a larger set of fields that were archived for that, including the ability to now start to look at a closer look at the Pele-Hoskins over this longer period. So out of this NWP perspective, just a couple quick points. We found this very informative in the developing of the sub-seasonal, seasonal forecast models in coupling to be able to have this NWP perspective. So we have been running this FIM model using the different dynamical coordinate core, but using the physics otherwise, same initial conditions, and able to show some improvements overall in the Northern Hemisphere over the year 2015, and especially in the Arctic, seeing improvements there that we attribute to the use of the dynamic core and the more uniform grid over the Arctic. We also found out of this NWP testing here great sensitivity to gravity wave drag, and so these actually are now coloring what the next steps need to be taken on, because we found that when we were able to use gravity wave drag with parameters that were commensurate with those in the high-resolution GFS, that we actually were able to get this improvement if we used other values there that were recommended for coarse resolution. Somewhat poor results. So the initial test in our hindcast actually used this poor result, so that's one of the signals here, but to have this intercomparison back and forth with NWP has been helpful. And one last issue is that there's been an issue in the NWP world with the global model ensemble at NCEP, and also with the ensemble as well as the deterministic model, and having a warm, dry bias. This is actually looking at relative humidity bias here overall. And getting this, it was found that the FIM model was able to avoid that, but it was able to identify simply by using land use parameters from the more recent satellite MODIS fields. That actually eliminated that overall. Those actually, the MODIS is in the intercomparison here. So our overall blocking behavior, first of all, just want to contrast these two waves that Tim Woolings did bring up here. The Tibaldi-Molteni index is actually more looking at a middle troposphere reversal of the flow, whereas the Peli-Hoskins is really more focusing on the dynamic tropopause determined by the PV = 2 surface here. And so in the Peli-Hoskins index, one other key difference is that there's this latitudinal difference as a function of longitude here, using the favored jet latitude. And out of that, what Peli-Hoskins found is that there is many fewer frequency for the Pacific blocks versus the Atlantic blocks. Using this dynamic tropopause block definition really focuses more on the European Atlantic blocks here. So now we go to, I guess, some of our first results. This is actually looking now at Peli-Hoskins blocking frequency here. And this is actually using a color scale. And you can see, and forgive us for commenting this out here, but this is showing a relatively constant frequency over time. This is actually looking at the forecast duration out to 30 days from 0 days right here. And this is more of a classic depiction of the same result here, looking at the frequency from the analysis with the black line here versus the model going out to 1 week, 2 weeks, 3 weeks, and 4 weeks. And there's an indication here of a strong over-forecasting according to Peli-Hoskins. And we actually have been able to see, though, there's some kind of shift in the definition of the dynamic tropopause and going to the isentropic coordinates. So this is a field of the theta on the PV2 surface from last night used in a FIM model run. And I'm going to contrast here versus what this looks like in a 6-hour forecast. So the definition sharpens up. This is actually our main block in the global circulation right now. It's over Asia, about 50 degrees east, north of the Caspian Sea. And so I'm just going to toggle back and forth here, the sharpening of this particular blocking situation going into the isentropic representation. So obviously this is going to be part of what we're going to be looking at here in identifying is in a more of an isentropic structure, is this really the true climatology or not? So also now a first comparison between the FIM and the CFS version 2. On the right here is looking at the climatology, or actually the 15-year or 13-year rerun here. Again, the black is the observed frequency as a function of latitude, and actually some moving up and down, a little bit of over forecasting in the Atlantic blocks going out to 4-week forecast, but really holding fairly close over a little of the latitude shift. The FIM, using this representation, is under forecasting both, I guess, the Atlantic blocks in particular, but now this is using this middle troposphere measure with the Tibaldi-Molteni. Regarding MJO frequency, again, a very initial look at this. So we're looking at the frequency, actually the forecast RMS error here of the MJO index, and this is actually looking at FIM versus CFS over the same period and showing a fairly similar lead time here versus the RMS, so it's slightly larger in FIM versus CFS. So this is, again, an initial look here, so relatively commensurate overall. And then looking at the correlation, again, in the MJO, relative similarity between these two models here right now. Some of the numerical processing is not quite done in common yet between these two. We've also been able to start some key case study comparisons here with and without coupling. There's some question in the week 3, week 4 whether coupling is necessary at all or not. So looking at some of these dynamo cases, and what we found is that some of the stronger cases that having ocean coupling seems to be critical. Having some of the weaker cases, that may not be the case. So that is an open question here, but certainly finding in some of these week 3, week 4 cases with MJO, having coupling is critical. Regarding stratospheric warming, which again is hypothesized as a key aspect, and again, the focus of our study here is breaking it down into these processes to look at predictability there. This is actually looking at the observed Northern Hemisphere 10 hectopascal fields over the last 15 or 16 years here. And this actually is looking at both the mean 10 hectopascal wind here, where it goes negative in the winter time. That's considered to be one of these stratospheric warming events. And we've also compared that with a maximum temperature in the Arctic region, again at 10 hectopascals. And we see there's often a coincidence between these warming events that take place. And so this is just identifying 9 out of the 15 years had some kind of significant warming overall. So we looked here at the yearly frequencies, a function of forecast duration going up to 32 days. So the 9 out of 15 here, about 60% overall. I had some kick up here in the initial very short forecast, but overall seeing a consistency and frequency of these stratospheric events. Again, it's a very initial look at this from the FIM field. We're able to look at this with the archiving of the stratospheric fields in that. We've looked at individual cases. One of them that occurred here from a stratospheric warming event was late winter 2 years ago in March. A major split of the whole stratospheric vortex that took place here, moving from this kind of asymmetric wave 1 configuration into a full split. And we found here, doing some initial experiments, that using the more PV conserving isentropic coordinate was able to get a forecast of the full intensity of this flow reversal in the stratosphere from using the isentropic coordinate versus a similar version of the FIM model in which we're able to match the current sigma coordinate used commonly, certainly in the GFS and in many other models. This actually is a stratospheric event that took place just in the last few weeks here, looking at what took place on around the 8th, at which time there was actually a warming that took place in the 10 hectopascal temperature going above 0 Celsius here. And actually, this is actually looking at a sequence of FIM forecasts, atmosphere only, showing some predictability that from 2 weeks before here. This particular metric or event did not match the full flow reversal in the mean zonal wind at 10 hectopascals. So our last slide here, just to give this kind of a summary of this initial very preliminary look so far. The hypothesis remains here, which remains to be seen whether we can really link predictability overall. But some of these key results so far in case studies, the ocean coupling at week 3, week 4, necessary in some cases, not in others. The stratospheric event here improved by the vertical coordinate using the more quasi-Lagrangian coordinate. And then some of the NWP testing has been helpful for identifying gravity wave drag land surface issues. So we're just starting this study here with CFS version 2 FIM HICOM. Plan to bring in the other NMME models here and even to move toward the future NOAA global model in the future. But the door is open here, and actually welcome interaction with people that are listening right now to participate with us and ESPC colleagues in this area. Thank you.
Dan, thanks so much. Thanks for the tour through all the work you're doing in this S2S area. That's great. So are there any questions in the room? Or online, you can raise your hand virtually, let me know, or type in your text box. And also, I've, again, unmuted Tim and Hailan if either of you would like to ask Stan a question. Okay, I'm not seeing any questions at the moment, Stan. Okay, well, we're running a little long, so I guess we should wrap up. I want to thank all three speakers for really excellent talks across the board, some great discussion, and thank Jesse, Carmen, and ESBC for co-sponsoring this. And just as a heads up, our next webinar will be in March, and that's going to be looking at this kind of an exploration of opportunities in terms of seasonal predictability and prediction of coastal high water levels, so a very different change from the topic today. And so stay tuned for the date and time of that. So thanks again to Tim, Hailan, and Stan, and we'll see you next time.
Thanks very much.
Thank you.
Thank you. Bye, everybody.
Bye.
Thank you, guys. You're right. Yeah. Okay.